So let's get started. Again, our goal for today is to derive some area formulas for triangles, and we'll eventually get to parallelograms, and we'll use those to find missing areas, solve problems, etc. We'll define the area of a square, which is what you've always seen it to be the length of a side squared. Common units are inches squared, centimeters squared, miles squared, kilometers squared, any unit of length squared. It's a two-dimensional concept, so the units better reflect that as well as 2 dimensions. Okay. Area congruence, say if two figures are congruent, then they have the same areas. If two figures are congruent, then they have the same areas. And lastly, the area addition idea. It's nearly identical to the segment addition postulate, the arc addition postulate, the angle addition postulate. The area addition postulate here will say that an area is equal to the sum of its non-overlapping parts. We'll use this idea to help us derive more complex formulas and some formulas, some more complex formulas, some figures that we don't even have formulas for. But if we can break them into, if we can divide the figure, the polygon, into things we do know the areas of and just sum them together, then we can find the area of the whole figure. Okay. So we'll kind of be using this idea down the line. Further review, area of a rectangle. A rectangle is a quadrilateral with 4 right angles. Area is equal to its length times its width. Does anyone recall what the area of a triangle is? Joel. Base times height. I'm going to draw this kind of odd-looking triangle very deliberately here. I'm going to call this length the base. The nice thing about triangles is that you can choose any base, which is a side of the triangle. Pick any one of the 3 sides. As long as you define the height, which is the perpendicular distance from the side to the opposite vertex. Does anyone know another word for height? What is this segment I've drawn in that's the height? What's another word for it? Altitude. So for a triangle, it doesn't matter how you choose your base, as long as you pick which one you choose, which side you choose to be the base, as long as you pick the corresponding altitude. Okay. Also known as the altitude. Okay. Again, it doesn't matter. It could be the one that's on the left. You can very easily choose the one that's on the quote-unquote bottom. But keep in mind that you could just rotate the paper, and now that side you picked isn't on the bottom anymore. Now it's somewhere else. And in this case, I rotate it so that the one I chose is now on the bottom. It doesn't matter how you pick it as long as you pick a side and the corresponding altitude. Will give you the area of your triangle. My advice to you is when you're trying to find the area of a triangle, pick a base and a height that are convenient to you. So if you pick a side and you don't have an easy way to calculate what the altitude is, then don't pick that base. Pick a different side to be the base. Okay. So our game plan for the rest of today and the rest of this unit really is going to be to take these two basics and use them as building blocks. And we're going to divide more complex polygons into rectangles and or triangles, and just add their areas together. It's going to be our plan of attack for more complex polygons. So the area of this parallelogram is the same as the area of this rectangle you can construct by essentially chopping off this triangle and inserting it over here, which has dimensions of b times h. So the area of a parallelogram is the same as of that rectangle, which is the same as the base times the height. A pretty awesome formula for a seemingly complex figure. The area of a parallelogram is simply just the base times its height, because you can just reconstruct that parallelogram into a rectangle. So if you can deduce that your figure is in fact a parallelogram, then the area is a relatively simple thing to find. Just multiply a base times the height. Again, the base is any side of the parallelogram, and the height is the corresponding perpendicular distance between them, or the distance between the two bases that you choose. So in, like, say, figure A, the area in this case should be, if this is the base, this is the corresponding distance between the two. Area should just be 9 times 11, or 99 square units. Okay. B and C you can do on your own. I don't want to spend any time on those. It's another parallelogram and just a simple triangle. Let's have some fun with D then. D is not a parallelogram. D is not a rectangle, and D is not a triangle. D is actually a trapezoid, but we don't have a formula for trapezoids yet. So we're going to have to figure out a way to calculate the areas based on our plan of attack. Joel, what do you want to try?
Well, I would just make it into a rectangle and a triangle. Put it down right there, so that would be an altitude, so that'd be 6. And then since it goes over 10 and then it continues on the bottom is 12, so that makes the base of the triangle 2. And so now you just find both areas. So it's 60 for the rectangle and then 6 for the triangle.
Absolutely. Great job, Joel. Take this complex figure, break it into rectangles and triangles. The easiest way is to draw another height at this vertex to create a rectangle and a right triangle. And I'll add the two areas together. Area 1 plus area 2. Which through some calculating on your own, you can come up with, it should be 66 square units. Okay. In part E, we're going to need, again, this is not any of the figures we've already seen, so we want to divide this into figures so we can find the areas of. I see two relatively natural ways to break this. You could divide it along the line of symmetry that you could draw in. Unfortunately, this line of symmetry doesn't give us rectangles or triangles. So let's avoid using that one. What would be another way to divide this, Paige?
Like split it in rectangles
You could, I think someone last hour said you could cut the top off of this little house. And if you had a rectangle whose bases are 18, if this base is 18, what's the height? What's the length of the altitude with this corresponding base? 6, because this vertical distance is 6, so this vertical distance better be 6 as well. So if you think of the triangle, yeah, triangle is our first area, the rectangle is your second. You could add these together. And I think you get, what? You get 6 times 18 plus half times 6 times 18. Which I think is 162 square units, which is, yep, what I got last time. All right. Last but not least, we have a triangle here. So if we choose this as our base, then you get 36. So the area of this triangle should be half times 36 times 10. Giving you an area of 180 units squared.
Oh, is that perpendicular?
But doesn't it have to be base times height? Isn't 10 that outside piece?
Oh, this is in the height?
Yeah.
Oh, no. We should probably calculate the height then, huh? Yeah, we probably shouldn't use this then. How do we calculate the height? Here's a right triangle. With hypotenuse of 10, side of 6, calculate the height. You could use Pythagorean theorem, or you could know that this is a Pythagorean triple, the missing one being an 8. So maybe a much better way, maybe a correct way to find this area would be area is half times 36 times 8, which is 144. Yeah. That's a way better way to do it. Because the height is the perpendicular distance, not just a random side length.